Here is an overview of the placement of the electronics, which is the first step in completing the electronics portion of this build. Since every build could actually have different brands or different choices in which boards you use, or different power supplies, or different microcontrollers, this layout may be different for your printer, even if it is a Chiron conversion. Here are the components that I decided to use. This is the Chiron's original 24-volt power supply. It powers the bed, the octopus board, and the hot end. This is a 5-volt power supply that's actually used exclusively to power the Raspberry Pi. This here is the Chiron's original MOSFET heated bed control board, which is actually still controlled by the octopus's heated bed output signal, but it's actually powered from the power supply directly. I'm currently using a Raspberry Pi 3B. It's actually one that I had left over from a different project, and it actually works just fine for running Klipper. The control board I went with is the Octopus 1.1 from Big Tree Tech. It might actually be a little overkill for this build, since I'm only using 3 of the stepper drivers out of the 8 that it can use. But I got it on sale, so that's what I went with. And even though the Octopus 1.1 has native CANbus support built in, I still went with the U2C board, also from Big Tree Tech, as my CANbus bridge for the toolhead. After you've picked out which electronics you're going to use for your build, placing them will determine how your wires are run. In my case, I separated the power supplies up here and all the control boards down here. When I began the wiring section on this project, it was a bit overwhelming. There was a lot of stuff that I didn't know, and I didn't know where it had to go, and of course documentation online is a bit scattered, and there really isn't a lot about the Chiron specific conversion, just a lot about Ender conversions or the Voron Switchwire build itself. But even that, the wiring is pretty vague considering there are so many options with what kind of boards, what kind of microcontrollers, what kind of power supplies you're using. So this is only going to apply with what I have chosen to use. However, it seems to be a very common set of parts. To make it easier to build, what I did was focus on one piece at a time, in which case I started with the 120 volt power supply, which would be 240 or 250 volts if you're in other parts of the world other than the US. So, here we've got the power inlet and the switch. This was also retained from the original Chiron, and it goes in here, and of course the wires were pretty short, but I didn't want to bother resoldering them. I ended up using the Voron's Wago 221 lever lock printable holder that actually bolts to the aluminum extrusion. Very handy, and that actually will branch out your 120 volt lines and your ground to, if you have multiple power supplies, to each device. If you only have one power supply in your printer, it may be wise to just extend the wires with new wires directly from the power inlet. Of course, as a disclaimer, working with mains voltage is dangerous. If you do not feel comfortable or do not feel competent on doing this, please consult a professional. It may be noted I am an electrician as my normal day job, so this is well within my scope of work. Once the mains power has been wired in, then you can focus on the 24 volt power. The Octopus board uses separate inputs for the motors, or your steppers, power for the board itself, and heated bed power. This is in case you use different voltages other than the 24 volt supply. In the case of my build, everything is running on 24 volts except the Raspberry Pi. I actually used the same Wago printable component to use lever locks down here, and that actually distributes the positive and negative of the 24 volt to both the Octopus inputs, but also the heated bed input for, well, the heated bed MOSFET controller, which, and the other end, that the output goes directly to the heated bed. And the small control wire, right here, which was also original to the Chiron, goes over to the bed output, and that uses a 24 volt signal to trigger the MOSFET to switch on and off at the desired rate. As for the Raspberry Pi, it's powered from 5 volts. Now you could go directly to the GPIO 5 volt pins, but that doesn't have the overvoltage protection like the USB port does. So what I did was I actually cut a USB cable, at least the large end, and stripped it out and landed it right on the 5 volt power supply. Sorry, can't really see it in this angle. Yeah. There you go. 5 volts right there. If you're planning to use CANbus for your tool head, like I did, the CANbus bridge board, or the U2C in this case, actually gets its main power from 24 volts into these inputs right here. The USB is actually sent to the Raspberry Pi, and that's how it is getting its data. And of course the tool head gets its power through this connector, or this one, or this one. There's actually a few choices depending on what kind of connector you use. I found this one easiest to be pinned with a large gauge of wire. And of course the build wouldn't be complete without cooling fans. I'm not sure if these are going to be sufficient for the build, but so far during my testing they have been. I actually ran it a little bit without the cooling fans. Also, I printed a little fan funnel to direct the airflow directly to the stepper drivers, considering they were actually getting quite hot without the fan blowing on them. And I actually had some skipped steps and had some layer shifting. This helped a lot. You can, of course, power the fans either from the Octopus or your controller board of choice. If it has extra fan pins, I did then on this side. The ones on the other side are actually powered directly from the power supply. Then, of course, you have choices in stepper drivers. There's multiple brands, multiple voltages. I actually went with the TMC 2209. They are the silent stepper drivers that seem to be the most popular to use. Once you have put your stepper drivers in whatever mode you are using, of course you have to run the cabling to the steppers. Now I didn't pin my own. I bought a kit that were pre-terminated at each end that matched. And that actually kind of complicated my build a little bit, considering the wires needed to be flipped at the ends. They were not the correct pinout. And what I mean by that is that even though these were the supposedly pre-made connectors, and they did have the correct connectors to fit the steppers on them, they're actually like flip-flopped. I don't know how you'd call that, but you can see here's one that I had corrected, and actually it basically passes straight. There's no flipping, where this one, this is how they all came in the package. The black on the outside actually crosses over, goes to the opposite side middle, and then likewise with the blue, which is in the middle here, crosses over to the other side middle. And what that did was, when I was trying to do my very initial homing, the stepper motors would vibrate a bunch and it would give me an error and Klipper would crash. So the solution to that, you can actually pop these little pins out with a very fine screwdriver or a blade of a knife if you're careful, tug on the wires to pop them out, and then put them in the correct order that works for your steppers. But that may or may not work for everyone's steppers or stepper drivers, so check with the configuration you're using. Wire management. I'm mediocre, I would say. It would be a lot better if I was better at crimping, but I used a lot of really long pre-crimped stepper wires and USB cables, and of course that leaves you with a bunch of slack. You can kind of bundle it up and zip tie it down. There are several printable options for cable management clips and brackets and all kinds of cool stuff. I found a few that I liked and used them. Yeah, so as long as you keep them out from getting in the way of moving parts, you're probably fine. USB cables. In my case, they were actually necessary for running the Pi to the Octopus board and the Pi down to the U2C board, which is for CANbus. You can actually see it right here. It zigzags its way over, goes to there. That sends the data it needs to be controlled, and of course likewise for the U2C board going down to here. This USB, of course, is just for the 5-volt power to power the Pi. This is the EBB36 by Big Tree Tech. It's actually a CANbus board for the toolhead. The orientation I have it mounted, of course, is not within the original design. I rotated it 90 degrees to actually have better clearance underneath the belts. Of course, this was only with the help of my modified STL files for the cable departure angle. Rather than going straight up and out, I had it go backwards at about a 45-degree angle, and then I had to lose some Z height. Alright, well, here's the first benchy, well, not the first, but the first finished benchy after the conversion has been done. And this compares to the one that I printed before tearing down the original Chiron. Now, I didn't use the same filament because I actually ran out of this one, so it's not exactly a fair comparison. Plus, since I had to basically create an entirely new slicer profile, I'm not sure it's a really fair comparison there either. However, they are both PLA. They are both printed at 200% scale because of the 0.8mm nozzle that I'm using. Pretty much the same settings. Anyways, I noticed that I still get the little, I don't know what you'd call it, the overhang troubles on the bow. I might have to change the temperature settings because I'm actually still using the same temperature settings as before and same cooling settings. Most of the surfaces look pretty good though. Might have been an improvement, but it's really hard to tell. I can tell you the smokestack actually looks better. A little bit of less stringiness on the newer one. So basically I need to do a lot more tuning, but I think I've mentioned before in my previous video, this is actually the first printer I've ever used Klipper on, and really it's quite a learning curve if you've never done it before.